Hi everyone. So by now you have probably heard of ChatGPT. It has taken the world and the AI community by storm. And it is a system that allows you to interact with an AI and give it text-based tasks. So for example, we can ask ChatGPT to write us a small haiku about how important it is that people understand AI, and then they can use it to improve the world and make it more prosperous. So when we run this, AI knowledge brings prosperity for all to see, embrace its power. Okay, not bad. And so you could see that ChatGPT went from left to right and generated all these words sort of sequentially. Now, I asked it already the exact same prompt a little bit earlier, and it generated a slightly different outcome. AI's power to grow, ignorance holds us back, learn, prosperity waits. So pretty good in both cases and slightly different. So you can see that ChatGPT is a probabilistic system, and for any one prompt, it can give us multiple answers, sort of replying to it. Now, this is just one example of the prompt. People have come up with many, many examples, and there are entire websites that index interactions with ChatGPT. And so many of them are quite humorous. Explain HTML to me like I'm a dog. Write release notes for Chess 2. Write a note about Elon Musk buying a Twitter, and so on. So as an example, please write a breaking news article about a leaf falling from a tree. In a shocking turn of events, a leaf has fallen from a tree in the local park. Witnesses report that the leaf, which was previously attached to a branch of a tree, detached itself and fell to the ground. Very dramatic. So you can see that this is a pretty remarkable system, and it is what we call a language model, because it models the sequence of words or characters or tokens more generally, and it knows how sort of words follow each other in English language. And so from its perspective, what it is doing is it is completing the sequence. So I give it the start of a sequence, and it completes the sequence with the outcome. And so it's a language model in that sense. Now, I would like to focus on the under the hood components of what makes ChatGPT work. So what is the neural network under the hood that models the sequence of these words? And that comes from this paper called Attention is All You Need. In 2017, a landmark paper in AI that produced and proposed the transformer architecture. So GPT is short for generatively pre-trained transformer. So transformer is the neural net that actually does all the heavy lifting under the hood. It comes from this paper in 2017. Now, if you read this paper, this reads like a pretty random machine translation paper, and that's because I think the authors didn't fully anticipate the impact that the transformer would have on the field. And this architecture that they produced in the context of machine translation, in their case, actually ended up taking over the rest of AI in the next 5 years after. And so this architecture with minor changes was copy-pasted into a huge amount of applications in AI in more recent years. And that includes at the core of ChatGPT. Now, what I'd like to do now is I'd like to build out something like ChatGPT. But we're not going to be able to, of course, reproduce ChatGPT. This is a very serious production-grade system. It is trained on a good chunk of internet, and then there's a lot of pre-training and fine-tuning stages to it, and so it's very complicated. What I'd like to focus on is just to train a transformer-based language model. And in our case, it's going to be a character-level language model. I still think that is very educational with respect to how these systems work. So I don't want to train on a chunk of internet. We need a smaller dataset. In this case, I propose that we work with my favorite toy dataset. It's called Tiny Shakespeare. And what it is basically, it's a concatenation of all of the works of Shakespeare, in my understanding. And so this is all of Shakespeare in a single file. This file is about 1 megabyte, and it's just all of Shakespeare. And what we are going to do now is we're going to basically model how these characters follow each other. So for example, given a chunk of these characters, like this, given some context of characters in the past, the transformer neural network will look at the characters that I've highlighted and is going to predict that G is likely to come next in the sequence. And it's going to do that because we're going to train that transformer on Shakespeare. And it's just going to try to produce character sequences that look like this. And in that process, it's going to model all the patterns inside this data. So once we've trained the system, I'd just like to give you a preview, we can generate infinite Shakespeare. And of course, it's a fake thing that looks kind of like Shakespeare. Apologies for there's some jank that I'm not able to resolve in here, but you can see how this is going character by character, and it's kind of like predicting Shakespeare-like language. So, verily, my lord, the sights have left thee again, the king, coming with my curses with precious pale. And then Tranio says something else, etc. And this is just coming out of the transformer in a very similar manner as it would come out in ChatGPT. In our case, character by character. In ChatGPT, it's coming out on the token by token level, and tokens are these sort of like little subword pieces. So they're not word level, they're kind of like word chunk level. And now I've already written this entire code to train these transformers, and it is in a GitHub repository that you can find, and it's called NanoGPT. So NanoGPT is a repository that you can find on my GitHub, and it's a repository for training transformers on any given text. And what I think is interesting about it, because there's many ways to train transformers, but this is a very simple implementation. So it's just 2 files of 300 lines of code each. One file defines the GPT model, the transformer, and one file trains it on some given text dataset. And here I'm showing that if you train it on an open web text dataset, which is a fairly large dataset of web pages, then I reproduce the performance of GPT-2. So GPT-2 is an early version of OpenAI's GPT from 2017, if I recall correctly. And I've only so far reproduced the smallest 124 million parameter model. But basically, this is just proving that the code base is correctly arranged. And I'm able to load the neural network weights that OpenAI has released later. So you can take a look at the finished code here in NanoGPT. But what I would like to do in this lecture is I would like to basically write this repository from scratch. So we're going to begin with an empty file, and we're going to define a transformer piece by piece. We're going to train it on the tiny Shakespeare dataset, and we'll see how we can then generate infinite Shakespeare. And of course, this can copy paste to any arbitrary text dataset that you like. But my goal really here is to just make you understand and appreciate how under the hood ChatGPT works. And really all that's required is a proficiency in Python and some basic understanding of calculus and statistics. And it would help if you also see my previous videos on the same YouTube channel, in particular my Make More series, where I define smaller and simpler neural network language models. So multi-allelic perceptrons and so on. It really introduces the language modeling framework. And then here in this video, we're going to focus on the transformer neural network itself. Okay, so I created a new Google Colab Jupyter notebook here. And this will allow me to later easily share this code that we're going to develop together with you so you can follow along. So this will be in the video description later. Now, here I've just done some preliminaries. I downloaded the dataset, the tiny Shakespeare dataset, at this URL, and you can see that it's about a 1 megabyte file. Then here I open the input.txt file and just read in all the text as a string, and we see that we are working with 1 million characters roughly. And the first 1,000 characters, if we just print them out, are basically what you would expect. This is the first 1,000 characters of the tiny Shakespeare dataset, roughly up to here. So far so good. Next, we're going to take this text, and the text is a sequence of characters in Python. So when I call the set constructor on it, I'm just going to get the set of all the characters that occur in this text. And then I call list on that to create a list of those characters instead of just a set, so that I have an ordering, an arbitrary ordering. And then I sort that. So basically we get just all the characters that occur in the entire dataset, and they're sorted. Now the number of them is going to be our vocabulary size. These are the possible elements of our sequences. And we see that when I print here the characters, there's 65 of them in total. There's a space character, and then all kinds of special characters, and then capitals and lowercase letters. So that's our vocabulary, and that's the sort of like possible characters that the model can see or emit. Okay, so next we would like to develop some strategy to tokenize the input text. Now, when people say tokenize, they mean convert the raw text as a string to some sequence of integers according to some according to some vocabulary of possible elements. So as an example, here we are going to be building a character level language model, so we're simply going to be translating individual characters into integers. So let me show you a chunk of code that sort of does that for us. So we're building both the encoder and the decoder. And let me just talk through what's happening here. When we encode an arbitrary text, like hi there, we're going to receive a list of integers that represents that string. So for example, 46, 47, etc. And then we also have the reverse mapping. So we can take this list and decode it to get back the exact same string. So it's really just like a translation to integers and back for arbitrary string. And for us, it is done on a character level. Now, the way this was achieved is we just iterate over all the characters here and create a lookup table from the character to the integer and vice versa. And then to encode some string, we simply translate all the characters individually, and to decode it back, we use the reverse mapping and concatenate all of it. Now, this is only one of many possible encodings or many possible sort of tokenizers, and it's a very simple one. But there's many other schemas that people have come up with in practice. So for example, Google uses a sentence piece. So sentence piece will also encode text into integers, but in a different schema and using a different vocabulary. And sentence piece is a subword sort of tokenizer. And what that means is that you're not encoding entire words, but you're not also encoding individual characters. It's a subword unit level. And that's usually what's adopted in practice. For example, also OpenAI has this library called TickToken that uses a byte pair encoding tokenizer. And that's what GPT uses. And you can also just encode words into, like hello world, into lists of integers. So as an example, I'm using the TickToken library here. I'm getting the encoding for GPT-2, or that was used for GPT-2. Instead of just having 65 possible characters or tokens, they have 50,000 tokens. And so when they encode the exact same string, hi there, we only get a list of 3 integers. But those integers are not between 0 and 64. They are between 0 and 50,256. So basically you can trade off the codebook size and the sequence lengths. So you can have very long sequences of integers with very small vocabularies, or you can have short sequences of integers with very large vocabularies. And so typically people use in practice these subword encodings, but I'd like to keep our tokenizer very simple. So we're using character level tokenizer. And that means that we have very small codebooks. We have very simple encode and decode functions, but we do get very long sequences as a result. But that's the level at which we're going to stick with this lecture because it's the simplest thing. Okay, so now that we have an encoder and a decoder, effectively a tokenizer, we can tokenize the entire training set of Shakespeare. So here's a chunk of code that does that. And I'm going to start to use the PyTorch library, and specifically the torch.tensor from the PyTorch library. So we're going to take all of the text in Tiny Shakespeare, encode it, and then wrap it into a torch.tensor to get the data tensor. So here's what the data tensor looks like when I look at just the first 1,000 characters, or the 1,000 elements of it. So we see that we have a massive sequence of integers, and this sequence of integers here is basically an identical translation of the first 1,000 characters here. So I believe, for example, that 0 is a new line character, and maybe 1 is a space. Not 100% sure. But from now on, the entire data set of text is re-represented as it's just stretched out as a single very large sequence of integers. Let me do one more thing before we move on here. I'd like to separate out our data set into a train and a validation split. So in particular, we're going to take the first 90% of the data set and consider that to be the training data for the transformer. And we're going to withhold the last 10% at the end of it to be the validation data. And this will help us understand to what extent our model is overfitting. So we're going to basically hide and keep the validation data on the side, because we don't want just a perfect memorization of this exact Shakespeare. We want a neural network that sort of creates Shakespeare-like text. And so it should be fairly likely for it to produce the actual, like, stowed away true Shakespeare text. And so we're going to use this to get a sense of the overfitting. Okay, so now we would like to start plugging these text sequences or integer sequences into the transformer so that it can train and learn those patterns. Now, the important thing to realize is we're never going to actually feed the entire text into the transformer all at once. That would be computationally very expensive and prohibitive. So when we actually train a transformer on a lot of these datasets, we only work with chunks of the dataset. And when we train the transformer, we basically sample random little chunks out of the training set and train on just chunks at a time. And these chunks have basically some kind of a length and some maximum length. Now, the maximum length typically, at least in the code I usually write, is called block size. You can find it under different names like context length or something like that. Let's start with the block size of just 8. And let me look at the first train data characters, the first block size +1 characters. I'll explain why +1 in a second. So this is the first 9 characters in the sequence, in the training set. Now what I'd like to point out is that when you sample a chunk of data like this, so say these 9 characters out of the training set, this actually has multiple examples packed into it. And that's because all of these characters follow each other. And so what this thing is going to say when we plug it into a transformer is we're going to actually simultaneously train it to make prediction at every one of these positions. Now, in a chunk of 9 characters, there's actually 8 individual examples packed in there. So there's the example that in the context of 18, 47 likely comes next. In the context of 18 and 47, 56 comes next. In the context of 18, 47, 56, 57 can come next, and so on. So that's the 8 individual examples. Let me actually spell it out with code. So here's a chunk of code to illustrate. X are the inputs to the transformer. It will just be the first block size characters. Y will be the next block size characters. So it's offset by 1. And that's because Y are the targets for each position in the input. And then here I'm iterating over all the block size of 8. And the context is always all the characters in X up to T and including T. And the target is always the Tth character, but in the targets array Y. So let me just run this. And basically it spells out what I said in words. These are the 8 examples hidden in a chunk of 9 characters that we sampled from the training set. I want to mention one more thing. We train on all the 8 examples here with context between 1 all the way up to context of block size. And we train on that not just for computational reasons because we happen to have the sequence already or something like that. It's not just done for efficiency. It's also done to make the transformer network be used to seeing contexts all the way from as little as 1 all the way to block size. And we'd like the transformer to be used to seeing everything in between. And that's going to be useful later during inference because while we're sampling, we can start the sampling generation with as little as 1 character of context. And the transformer knows how to predict the next character with all the way up to just context of 1. And so then it can predict everything up to block size. And after block size, we have to start truncating because the transformer will never receive more than block size inputs when it's predicting the next character. Okay, so we've looked at the time dimension of the tensors that are going to be feeding into the transformer. There's one more dimension to care about, and that is the batch dimension. And so as we're sampling these chunks of text, we're going to be actually, every time we're going to feed them into a transformer, we're going to have many batches of multiple chunks of text that are all like stacked up in a single tensor. And that's just done for efficiency, just so that we can keep the GPUs busy, because they are very good at parallel processing of data. And so we just want to process multiple chunks all at the same time. But those chunks are processed completely independently. They don't talk to each other and so on. So let me basically just generalize this and introduce a batch dimension. Here's a chunk of code. Let me just run it, and then I'm going to explain what it does. So here, because we're going to start sampling random locations in the dataset to pull chunks from, I am setting the seed so that in the random number generator, so that the numbers I see here are going to be the same numbers you see later if you try to reproduce this. Now the batch size here is how many independent sequences we are processing every forward-backward pass of the transformer. The block size, as I explained, is the maximum context length to make those predictions. So let's say batch size 4, block size 8, and then here's how we get batch for any arbitrary split. If the split is a training split, then we're going to look at train data, otherwise at val data. That gives us the data array. And then when I generate random positions to grab a chunk out of, I actually generate batch size number of random offsets. So because this is 4, ix is going to be 4 numbers that are randomly generated between 0 and len of data minus block size. So it's just random offsets into the training set. And then x's, as I explained, are the first block size characters starting at I. The y's are the offset by 1 of that, so just add +1. And then we're going to get those chunks for every one of integers I in ix and use a torch.stack to take all those one-dimensional tensors, as we saw here, and we're going to stack them up as rows. And so they all become a row in a 4x8 tensor. So here's what I'm printing then. When I sample a batch xb and yb, the inputs to the transformer now are, the input x is the 4x8 tensor, 4 rows of 8 columns, and each one of these is a chunk of the training set. And then the targets here are in the associated array y, and they will come in to the transformer all the way at the end to create the loss function. So they will give us the correct answer for every single position inside x. And then these are the 4 independent rows. So spelled out as we did before, this 4x8 array contains a total of 32 examples, and they're completely independent as far as the transformer is concerned. So when the input is 24, the target is 43, or rather 43 here in the y array. When the input is 24, 43, the target is 58. When the input is 24, 43, 58, the target is 5, etc. Or like when it is a 52, 58, 1, the target is 58. Right, so you can sort of see this spelled out. These are the 32 independent examples packed in to a single batch of the input x, and then the desired targets are in y. And so now this integer tensor of x is going to feed into the transformer, and that transformer is going to simultaneously process all these examples and then look up the correct integers to predict in every one of these positions in the tensor y.